Hello everyone, my name is Matthew and welcome back. Today we're going to be doing the Count Good Nodes question in the Trees module. So again, before we get started, I would just like to lay out our steps for solving these problems. So one, understand it, and then the second one, come up with a solution, and then the last step, of course, is always just to optimize. All right, so without any further ado, let's just get into the question. So question title, count good nodes, and the problem statement. So given a binary tree root, a node x in the tree is named good if the values of x, or if the value of x is even, and in the path from root to x, there are no nodes with a value less than x. Okay, and then we just need to return the number of good nodes in the binary tree. So if we look at this first example, we're given this binary tree here. This is how it's represented, and the output is 3. So the explanation says that there's 3 nodes at the bottom level, which are even, and there exists no nodes with lesser value on their respective root paths. And it says that they're 2, 0, and 0. And if we look at these paths, there's no node with a value less than 2 on the path from here all the way up to the root. And we also have to take into consideration that it's even, which is what makes it good. And we see that the same happens for 0 and this other node with value 0, right? And if we look at this last node here, it's even, but this number 1 has a value less than it, so it can't be good. So it makes sense so far. Now let's go ahead and look at the second one. We have this binary tree here, 2, 0, 2, and the output is again 3. And this time the explanation says that the root node is allowed to be a good node itself, because it's the only node on the path and it's also even. So that's just one thing to take into consideration with our solution. And then we also see that 0 and 2 are again good nodes. And then if we take a look at this last example, we see that there are 0 good nodes. And now that we have this intuition of what a good node is, we can kind of just check, okay, well, is it even first? If it doesn't satisfy that, then we don't have to check anything else. So we can look at 3, it's not even. We can look at 6, we know that it's even. However, on the path from itself to the root node, there's the root, which is less than 6. So that violates the good node property, so it's not good. And then we look at the last node, and it's not even, so it can't be good. And so that's really just the example so far. And let's just look at the constraints. So there's some bounds on the values of the tree node values, and the given root will never be null. So we'll know that we're always going to have at least one node. So that seems to be the problem so far. I think everything makes sense. We understand it. Let's just come up with a solution first. So let's just go solution 1, right? So like we said in the examples, we kind of got this intuition of what made a node good. We just had to check if it was even and if the path from the root to x is, or if they're on the path from root to x, there are no nodes with a value less. So it seems as if we want to check the entire tree for these good nodes. And remember, we learned there are several ways to traverse a tree. You could do a depth first search or a level order traversal. In this case, let's just do a depth first search traversal, right? So we're going to do a DFS, and that just ensures that we check the entire tree. Now, whenever we do have a node itself, we're gonna check if it's even. So check if a node is even. But now we're at this point where, okay, the DFS just gives us the node and nothing else. So remember, we want to check if there's no node with a less value than x on the path from itself to the root. So what we're also going to want to do with the DFS is supply the path for each node from itself to the root, and from there we can then check if the second condition is satisfied. So to check if node is satisfies second condition. And if it does, well, then we just increment the good nodes value or variable that we're gonna have, increment good nodes. And once we're done with the depth first search, we've checked every single node. So we've successfully checked all the good nodes, and then we just return the good nodes. So this seems like a pretty simple solution, pretty straightforward. It's basically just built off of some sort of traversal algorithm. So I think let's just, without further ado, let's get into it. So like we said, we're going to want a variable called good nodes. So let's just say good nodes, and we're going to initialize that to be 0. So good nodes 0. And since we're doing a depth first search traversal, you can either do this recursively or iteratively. I'm just going to do it iteratively. So we're going to want a stack, and within this stack, we're going to want a pair, and this pair is going to hold a tree node. And actually, before we get into it, let's just look at the tree node class real quick. So it has this value, right? And then it has children for the left and the right. And this is just a simple constructor. So now that we understand that, we can store the tree node in this pair. And then, like we said, since we also want to have the path within this depth first search traversal, we can represent the path with just a vector of tree nodes. And this should be the entire stack, and let's just call this S, right? And before we go any further, let's just include stack. Okay, and I think we just need one more angle bracket, right? Yeah. So that should be all the data structures I think we need for this. And before we go into it, into the depth first search traversal, we're going to want to push the root node into it. So you can see that this is a pretty lengthy statement. So I'm just going to make a simple function that just pushes something onto the stack, so I don't have to say this entire thing every single time. So we're just going to call this push pair, and it's just going to take in this stack, and we're just going to have a reference to it, S, and then we're just going to want a tree node, and then a path, right? So std vector tree node, let's call this path. Yeah, and this is just pretty lengthy, so I'm just going to go like that. So within this, we're just going to go s.push, and then we're just going to make a pair, like we said, tree node, like that. Oop, there we go. Yeah, and then it'll just be the node itself and the path. Okay. Yeah, so then I'm going to go push pair the stack, the root, and remember, like we said, the path from the root to itself is just itself, so we're going to make a vector with the root itself. Tree node, yeah, root. All right. So now that we've got that under the way, we have this start of a depth first search traversal. We're just going to traverse until the stack is not empty. And what we're going to want to do first is just get the tree node that we're currently visiting. So s.top, and then front, or I'm sorry, not front, first. And then, okay, yeah. I forgot to name this. Okay, node is just s.top first. And then, okay, it says there's an error here. So it says, did I just name this wrong? Okay, no, I didn't. Oh, I'm being silly. Okay. There you go. Okay, so that's the how we get the tree node, and then we get the path itself, tree node, and I'm just going to call this path s.top.second. And once we do that, we're going to pop that pair off of the stack. Okay, so now that we have this, like we said, we're going to want to check if it's a good node. So if it satisfies both of these conditions, then perfect. We increment the good nodes count. So first we're going to want to check, is it even? So if if node.val or node val, if that mod2 is equal to 0, and like we said, if it satisfies the second condition, so if there's no node with a value less than x on the path. So if it is the smallest in the path, let's just create some sort of abstraction for now. So node and then path. And let's just pretend that this function gives us the, it returns true if it is the smallest and false if it isn't. So clearly if it is the smallest, then it satisfies the good node condition given that it's even. So given that, we're just going to increment good nodes plus plus. All right. And now that we've satisfied that condition, we're also going to want to just, actually no, that's all we have to do so far. Yeah. So now, like we said, since this is the depth first search traversal, we're going to push the nodes onto the paths, or onto the stack themselves. So yeah, first we're going to want to push the left child in, and since we're not doing any checks here to check if the node itself is null, we're just going to do that when we add that into the stack. So if node left is not a null pointer, then what we're going to want to do is we're going to get this path, and we're going to append the node left onto the path. Right? Yeah. And then after that, we're going to say s-dot, or actually we're not going to do that. We're going to use this push pair method that we made. All right, and now you're starting to see how convenient it is for us. We don't have to type all that mumbo jumbo. And then new path. Push pair, yeah. And then once we do that, we're just going to, I think, what is it, pop back, yeah. We're just going to remove that node that we added to this path. Because there's also the case that the right node is not a null pointer. And so if it's not a null pointer, then it has a right child. So then we're going to want to push itself onto the node, or onto the path. And then essentially the same thing, except it's not really necessary to pop it back, but let's just do it just to be nice. All right. And yeah, I think that should just be the end of our depth first search traversal, right? Let's just go over this again. We get the first node, we get the top of the stack, then we pop it off. Then we're checking if it's a good node, and then all we're doing is just adding the children on and updating their respective paths. And we just continue that until we can no longer iterate through the stack because there's no nodes left. So with that being said, all we need to do is now just implement this is smallest path function. So like we said, this is smallest path will just return a boolean. So bool is smallest path, and we're just going to have a tree node and a vector of tree nodes, and let's just call this path. So I think this is pretty straightforward in our terms of implementation. All we're going to do is just check, does this node have the smallest value in the vector? So we can just do a simple for loop. So let's just go for each tree node, let's call it t in path, and then we're just going to say if node dot val is greater than t val, then we're going to return false, right? And so we say again, if there are no nodes with value less than x, and so clearly, if this is greater than some value, then t value has a lesser value than node.val. So we just return false, since it's not the smallest in the path. Otherwise, we return true, since it is. Yeah. So I think that should just be our entire function so far, then. Let's check it with a simple example, like example 1. So we get the first root, and it's 5. We push that onto the stack along with itself as the path, and then we start our depth first search traversal. So we're going to get it off the stack. Then we're going to check, is it even? And since it's not even, then we don't have to check for this is smallest path condition. And so now all we have to do is just add its children. Clearly, 5 and 3, they're not null pointers, so we're going to push those and their respective paths onto the stack. And so we'd check node right first, since it was popped, or since it was pushed last, and we'd go through the exact same thing, okay? So we'd take it off the stack. It's not even, so we don't increment good nodes. Now we just have to add its children. So we go to node left, and we add that, and we go to node right, we also add that. And then we go to node right again, do the exact same thing. It's not even. Now we add its children, but this time node left is a null pointer, so we don't add that, and all we do is just add the rightmost node, so 2. And then we go again into this stack, into this depth first search traversal. We take 2 off of the stack. Now we know that, okay, it does satisfy this condition, right? 2 is even. And then we check is smallest in the path. So then we go to this function, and the path should just be 2, 1, 3, and 5. So the first thing we'd compare it with is itself, and this condition wouldn't be satisfied. So then we go to 1, which is the next value on the path. Then we see here that, well, 2 is greater than 1, so clearly it's not the smallest in the path. And that's true if we look at the explanation. 2 is not included in the number of good nodes. So we return false, so good node is not incremented. And this time, since 2 is a leaf node, we can't add any of its children. So we go to 8 now, since that was the next on the stack. We see that it's even, but then again, our is smallest path says that 3 is less than 8. Okay, so now we add both of its children again, 0 and 0, and we now see that, okay, when we pop each of them off the stack, they're both even, and this is smallest path should say that 8, 3, and 5 are not greater than 0. Or I mean, they are greater than 0, but 0 is not greater than any of them, so that should return true, and we should see that both of these are the smallest in the path. And again, we don't do this adding of the children since they're both leaves. And this should just, again, go down all the way up to 2, and until we check it's even and it's the smallest in the path. So that was a bit of a long example, but it was basically just demonstrating that our algorithm should work. So enough talking, let's just see how good it actually is. And it says, its smallest path was not declared in the scope. Okay. Let's see. Is smallest path, node, and then path. So std vector tree node. Hold on. Okay, I think I just forgot to save it. Alright, I think, yeah, that's what happened. Alright, always remember to save your code. And it says segmentation violation signal. Okay, so this is good. Well, it's not good, but it shows that not perfect. And it says segmentation false. So there's probably some sort of error here going on with the memory. So let's just go ahead and check it out. Okay. if we bring that up again, it fails example 1. So it says that there are, or no, it actually fails example 3. So let's go ahead and see what happens there. So we push 3 onto the stack along with itself in the vector. Then we get the top stack. We get it from the top. 3 is obviously not even, so we check the, oh, I see. So we made an oopsie here. When we were pushing the pair, we were just pushing a null pointer onto the stack instead of node right. Yeah, and that would cause complications. So now let's see, does this pass? Okay. Oh, I think I forgot to save it. Oops. All right, perfect, see? Now, if your code doesn't work, don't freak out. Just look at it and see where it might go wrong, right? So with that being said, our algorithm works. We did face some technical difficulties, but we got it in the end. So like we said, all we have to do is just evaluate our algorithm now, right? How good is it in terms of runtime and in terms of space complexity? So let's just go ahead, say time. So we can just evaluate this step by step. So we're just initializing these nodes and we're pushing a pair onto the stack. Those are all O of 1 operations so far. And then we're doing this depth first search traversal. And remember, a depth first search traversal goes through every single node in the tree. So we can say that this depth first search traversal does O of n operations, right? O of n iterations. And then within this depth first search, let's just check each line. So these are all O of 1 operations as well. O of 1, and then we get to this is smallest path function, right? Clearly, if we evaluate the time complexity of this, we're iterating through every single node in this vector. So this is linear in terms of time complexity. This is smallest path, since it depends on the size of path, and we're only iterating through it once. So this is an O of n operation we're doing here, right? So let's just label that O of n. Then we check these, and we can see that these are all O of 1 operations, right? We're just appending something to the end, and then pushing it onto the stack, then removing it from the end, and then we're doing the same here. So this entire iteration is just O of n. And like we said, since a depth first search traversal is also O of n, within each iteration, we're doing an O of n, we're doing O of n iterations again. So we multiply those, and we see that the overall time complexity of this is O of n squared. And then if we look at the space complexity of this, we see that the stack has a pair, and each pair is the tree node and its respective path. And so usually, again, the path, or I think the space complexity of a depth first search is usually just O of n. And then we can also just sort of say a naive upper bound on this would also be O of n squared, since it also stores each node and its respective path. So space O of n squared. So in terms of time and space complexity, these are quadratic, so it might not be the best. And let's just see, like, right, let's go back to step 3, optimize. Is there any way we can sort of optimize the solution, make it better than O of n squared? Well, if we look at our algorithm again, and if we look at some potential bottlenecks, the only thing we're really seeing here is just this as smallest path, right? Everything else is constant time, everything else is perfect, except for this as smallest path. So if there's some sort of way we can reduce this to be O of 1, then we can better our time complexity and just have a better algorithm. So I think one thing that we can do is, instead of storing each path with every single depth first search traversal and checking naively, is this the smallest in the path, we can continuously update the smallest node in the path with each traversal, right? So like I said, 5, that's the only one in the path, so it's the smallest currently. And then when we add 3, well, we see that 3 is less than 5, so we say that 3 is the smallest in the path. Then we go to 1, 1 is less than 3, so 1 is the smallest in the path to the root. And then now we go to 2, and remember, instead of checking every single one, all we have to do is just check against the smallest in the path. And I think if it's greater than the smallest in the path, then there's a value with a node less, so it's not even. Otherwise, if we go something like here, 0, the smallest in the path would just be 3. 0 is less than 3, so it's a good node. And it's also even, so it's a good node, yeah. So that seems to be a simple optimization we can make, right? And it should reduce this O of n bottleneck down to O of 1, and theoretically, our time and space complexity should both be O of n, right? Since we would just be storing a pair with just an int instead of a vector. So let's just write that down again in case we get lost. Solution 2, do a DFS, and then store smallest int in path in stack. And then we can just, once again, do these. And like we said, this second condition will just be a lot quicker, since all we have to do is make one comparison. And then, like we said, increment good nodes. So it's pretty similar to our last one. It's actually, I think it's like pretty identical to our last algorithm, except this is smallest path comparison will just be a lot quicker now. So yeah, let's just start modifying our code. So like we said, all we're going to store in this stack is just an int. So we can go ahead and just say tree node and int. And let's just modify this now, our push pair. And let's just say it's an int. And this is just going to be an int called val. Let's just say it's that, yeah. And then we just got to go like this. Boop, okay. Val. And I think that should be okay, right? Yeah. Okay. Yes, okay. So we have the stack, and then we have a pair. It's a tree node, and it's an int. Go like this. And it's saying we have a little error. Okay. That's just me being silly again. All right. So yes, this algorithm, or this function, is relatively simple. All we're doing is pushing an int value along it, and right, like we said, it's the only path is itself, so we're pushing it along there. Okay, so that should just be these steps modified. Then we begin the depth first search traversal. So we get the node off the stack, and like we said, we're just going to get an int, and we're just going to call this min value, right, and then we pop it off. Then we're just going to check, is the node even? And instead of doing this is smallest path function, all we're going to do is check if node.val is less than or equal to the minimum value. And if it is, then perfect. There's no node with value less than x. And so, like we said, this is now just O of 1. And so before we get into adding the children, we're also going to want to adjust the minimum value, right? So min value is just the minimum between itself and the current value. Great. Now all we have to do is just do these adding of the children. So remember, we don't have a path anymore, so we're going to get rid of those statements. And like we said, we're going to add the node along with the smallest path. Boop and boop. All right. Perfect. So that seems to be the entire algorithm now. There's nothing else to modify. Yeah, and let's just check it again against a simple example. So given this example 2, let's see. All right, so good node 0, and then we initialize our stack, and then we push 2 along with its value onto the stack. Then we're going to get the node and the minimum value, which is itself. 2 is even, and 2 is equal to itself. So we increment the good nodes to be 1. Then we update min value, it stays the same, and we add its children. So then next we go to this value, and like we said, this is essentially equivalent. We get it off. 2 is even, and again, it's equal to 2, and then min value stays the same. And there are no more children, so at least no more children of 2, so we don't add anything. And then we go to the final node 0. 0 again, it's even, and it's less than 2, so we increment good nodes, and we also update min value. Then we have no more nodes to add, so it seems to be working, because then we just return 0. Yeah, and like we said, this gets updated to O of 1. So let's see truly how good our algorithm is. Let's see if it actually works. Fingers crossed. All right, perfect. Our algorithm works. And so yeah, that's sort of wraps up the problem on our count good nodes, right? If we think about it in terms of time, like we said, this is exactly the same, except we reduced that O of n operation to just be O of 1. So in terms of time complexity, this is just O of n. And like we said, we're no longer storing the path. So this is essentially just a normal depth first search traversal. And this is also just O of n. So that wraps up our question on trees. And I don't think there's any other way to sort of optimize this, right? If we want all the good nodes, we're going to have to check every single node. So doing a traversal of any sort it's inevitable. So the lowest bound should be of n, and same for the space complexity, since we've got to check every single one. So yeah, that's it for the question. Thank you for watching. Have a nice day.